In the last video, we discussed the construction and the main properties formation of depletion layer in a junction field effect transistor. Now we will discuss the drain characteristics, which are also called output characteristics of junction field effect transistor or JFET. In order to draw the drain characteristics of a junction field effect transistor, the circuit diagram is shown in figure 1a. This is an N-channel FET. The circuit diagram which we are discussing is for the N-channel FET. And as we know that the gate and source junction is always reverse biased. In the N-channel FET, the gate is P-type semiconductor and the channel is N-type semiconductor. In order to bias the gate and source junction in reverse mode, we have to connect the gate to the negative terminal of the battery and source to the positive terminal of the battery. So this is the reverse biasing of gate and source junction. And in the drain and source junction, since it is N-type semiconductor, so source is connected to the negative terminal and drain is connected to the positive terminal, so that the electrons are moving from source towards the drain and a current is flowing in the drain source circuit. The direction of flow of positive charge or the direction of flow of drain current is shown. The direction is shown in the figure. Now the gate voltage between gate and source is VGS and the voltage between drain and source is VDS. The output characteristics are the variation of the drain current with the variation in the drain and source voltage, that is VDS. In figure 1b, the characteristic curves for the characteristic curves or the output characteristics of JFET are shown, in which along the x-axis we have taken VDS and along the y-axis the variation of drain current is taken. And these curves which are shown in this diagram, the curves are for different values of VGS. For example, in the uppermost curve, VGS is plus 0.5 volt. Plus means it is VGS is forward biasing the gate and source junction. Though in practice it is never used. The forward bias is never used, but it is shown just to give an idea okay, what happens when the forward bias will be applied, though it is not used in any case. The second curve is for VGS equal to 0. Then VGS is -1, that is reverse bias of 1 volt is applied. Then reverse bias of 2 volt, then 3 volt, then 4 volt. In this manner, for different constant values of VGS, the variation of drain current is drawn against the variation of drain and source voltage, that is VDS. In order to understand the drain characteristics in detail, we are considering a single curve which is for VGS equal to 0. We have maintained the gate and source junction at 0 volt, or we can say that gate and source junction it is shorted. As we can see from the figure, when the drain source voltage, that is VDS, is increased from 0, the drain current is increasing sharply in a linear manner. It is increasing along a straight line. After a certain point, beyond the point A, the variation, the rate of increase of drain current is slightly reduced. So it is not in the form of a sharp increase or a linear variation, but it is in the form of a curve. This point A is known as the knee point, and after a certain point, that is the point B, the drain current becomes almost constant, independent of the variation in drain source voltage. It becomes absolutely constant. Whatever be the value of drain source voltage VDS, the drain current remains constant. And this voltage at which this phenomenon occurs is shown as VP. This voltage is VP and it is called pinch off voltage, and the point B is known as pinch off point. When the drain source voltage is increased to a very large value, then after that, if we are again increasing, continuously increasing the drain source voltage, then after some time the drain current becomes enormous and it is called breakdown region. And in practical cases, we do not increase VDS beyond a certain value, so that we are not encountering the breakdown region, because in the breakdown region the drain current becomes so heavy that it can damage the junction field effect transistor. Now, this curve, as we can see from this figure, it is divided into different portions. From O to A, this region is called the ohmic region. From A to B, this is called curve AB. And B to C is called pinch-off region or saturation region. And beyond point C, where it becomes, the current becomes too heavy to handle, this is called breakdown region. And this is the drain characteristic with shorted gate. It means that gate is directly connected to the source. Now we will discuss or try to understand different regions in which the drain characteristics of JFET are divided. The first region is the ohmic region or OA. We know that inside a FET there exists a depletion layer, and the width of the depletion layer depends upon the reverse bias which is being applied uh, between the gate and source, and it also depends upon the value of voltage which is being applied between drain and source. Since in this case we are considering the only the case of shorted gate, that is when VGS is 0, so we will consider the formation of depletion layer due to VDS only. And we know from our previous video that due to VDS, the shape of the depletion layer becomes like a wedge, or it is wedge shaped depletion layer. Now, when the value of VDS is small, or we are increasing VDS from 0, in that case the wedge shaped depletion layer will not come into existence, or we can say that the channel is totally open for the movement of the electrons. So when we are increasing the voltage VDS for smaller value, for its smaller values, then the current also increases linearly, like in an ohmic resistor. In a resistor, when we increase voltage, then the current increases in a linear manner, and it is called ohmic variation. So since the channel is behaving as a simple resistor, therefore the variation is also ohmic variation, so it is called ohmic region. Now when we are increasing VDS continuously and reach the point A, then we know that due to VDS, the wedge-shaped depletion layer comes into being. That is, the wedge-shaped depletion layer is forming, and the uh, width of depletion layer will swell up in the upper portion, and width of channel will decrease. So in this region, the increase in VDS has two two effects. The first effect is that due to the normal uh, nature of increasing the voltage, the current will try to increase because more electrons will be attracted towards the positive terminal. But on the same uh, but the same effect is also there, that with the increase in VDS, the width of depletion layer is also increasing. So it has a tendency of reducing the current. So two phenomena are occurring simultaneously. One is the increase in current, and the other is the decrease in current, which is due to depletion layer. So if we take the resultant of these two, then the net effect will be that with the increase in VDS, current ID will increase, no doubt, but it will increase at a reduced rate. Therefore, instead of getting a straight line, we will be getting a curve. And the point at which as we will discuss in the next portion, uh, this phenomenon occurs till pinch of voltage Vp, which we have shown in the previous slide. Now the pinch off region or the saturation region. This portion is denoted by BC in figure 2 in the previous slide. And in this region, what happens at a particular voltage Vp, which is shown as a pinch of voltage, the two effects of increasing VDS, that is, the first is due to increase in VDS, current will try to increase, and the second effect is that due to increase in VDS, current will try to decrease. And in this region or beyond Vp, these two effects counterbalance each other. That is, the increase in current will be counterbalanced by its tendency to decrease. And the net result is that with the increase in VDS, the current will neither increase nor decrease. That is, it will become absolutely constant. And the maximum value of current here is represented, which is a constant value, as shown in the, you can refer to the previous slide in the figure number 2. The maximum value of current which is constant is IDSS, or it is drain to source current with shorted gate. And this is applicable only for the case when VGS is 0. Shorted gate means 0. So IDSS, when we are referring, then this is the constant current or the maximum current for VGS equal to 0. In this figure, we have shown the state of affairs at pinch of voltage. The most important thing is that some people have a notion that at pinch of voltage the two depletion regions start to touch, but this is not the actual case. If at the pinch of voltage the two depletion layers touch each other, then the channel width will be 0, and when the channel width is 0, the current will be absolutely 0. But as we have seen that at pinch of voltage the current is not 0, but it is maximum, and the only noticeable thing is that it becomes constant. So we can say that in this region or in the saturation region, the depletion layers are not touching each other, but some width is present, some width of the channel is present through which the electrons are moving. The only thing is that as soon as the current tries to increase due to increase in VDS, it will also increase the width of the depletion layer so that its tendency to increase is counterbalanced by the tendency of the depletion layer to decrease the current due to the decrease in the width of the channel. So this point is to be noted that at pinch of voltage, the two depletion layers are not touching each other, but they are a slight distance apart. The only thing is that the channel width becomes minimum at this voltage or at pinch of voltage, or we can say throughout the saturation region. Now, we have seen that in the saturation region, the current becomes independent of the drain current becomes independent of VDS. So if we are increasing or decreasing VDS, the current will remain constant. So if we want to increase or decrease the drain current, the only option left is that of VGS. So we can say that in the saturation region, the drain current does not depend upon VDS, but it depends upon VGS. That is, if in this region, if we have to vary the drain current, then we have to increase or decrease the gate source voltage or the input voltage. And this is the reason why it is called field effect transistor. As I have mentioned in the previous lecture, that field effect transistor is a kind of transistor in which the output current can be controlled by the input field or input voltage. So now it becomes clear that if we have to increase or decrease the output current, then we can vary the input voltage or input field, which has a direct impact on the output current. Whereas in the conventional or BJT, bipolar junction transistor, the output current can be controlled by the input current. So this is the basic difference between JFET and BJT. Now again, we have to refer to figure 1B, where different drain characteristics are drawn. We can see there that if VGS is increased from 0 to -1 volt, or the reverse bias on the gate is increased, the drain characteristics are shifting downwards. That is, the maximum current or saturation current becomes lower. Again, if we increase the reverse bias from 1 volt to 2 volts, then it again will shift downwards. If we increase it from 2 volts to 3 volts, it will be decreased to a smaller value. And we can see that when the reverse voltage applied between the gate and source is 4 volt, then the saturation current or the current through the JFET becomes absolutely zero. And one thing is worth noting here, that if the pinch off voltage is 4 volt, that is for VGS equal to 0, if the pinch off voltage was 4 volt, that is if we have kept VGS at 0 and VDS we have made as 4 volt, then the drain current becomes absolutely constant. Now we can see that if this 4 volt, which is a pinch off voltage for VGS equal to 0, if this 4 volt is applied as reverse bias between gate and source, then it will make the drain current absolutely 0. It means that, and this voltage is called VGS off. So VGS off, which is making the drain current absolutely zero, and pinch off voltage, which is making the drain current maximum and constant, they are numerically equal. But the only thing is that VGS off is being applied as a reverse bias between gate and source, and pinch off voltage is being applied between drain and source. And again, the breakdown region is in the end of the characteristic. And at this point, due to very large high value of reverse bias between the PN junction, as it was discussed earlier, which is giving rise to the wedge-shaped depletion layer. For very high values of VDS, the depletion layer becomes too large, and when the reverse bias is very high, then avalanche effect occurs, and there is a breakdown of gate to source junction. Now figure number 4, the transfer characteristics of junction field effect transistor are shown. Transfer characteristics are the variation of the drain current with the variation in gate source voltage. As I have discussed in the previous slide, that the gate and source junction of a junction field effect transistor is always reverse biased. Therefore, the voltage VGS is shown on the negative side. Whether it is a P channel or N channel, in the transfer characteristic, VGS is always shown on the negative side, just to indicate that the gate and source junction is being reverse biased. Now, for drawing the transfer characteristics, we have to make VDS constant. That is, we have to put VDS at a constant value, and it is ensured that VDS is made constant at a value greater than the pinch of voltage, so that the FET is being operated at the saturation region, because the most useful uh, uh, region of a FET is the saturation region, in which it is being used as an amplifier. So we know that when at this point at the origin VGS is 0, and we know that when VGS is 0, the current is IDSS, because the FET is being operated in the saturation region. So the value of drain current is maximum, that is IDSS, the value of drain current with shorted gate. So at VGS equal to 0, the drain current is IDSS. And when the reverse bias is being increased, when the reverse bias between the gate and source junction is increased, the drain current reduces, it goes on decreasing, and at a certain point it becomes 0. As we can see here, the value of VGS at which the drain current becomes 0 is shown as VGS off. And it was mentioned in the earlier slide also that the value of VGS at which the drain current becomes 0 is called VGS off, and it is numerically equal to the pinch of voltage. It was also discussed in the earlier slide. Both are uh, having the same magnitude, but the only thing is that when it is applied as VGS, it is to be reverse biased, and for the drain and source voltage, it is applied in the normal manner. The other noticeable thing or important thing about the transfer characteristics is that if we take the lower values of VGS, these are the lower values of VGS, then the fall in current is more sharp. And as we are going towards the higher values of reverse bias, then the decrease in the drain current is slower. And as we are moving towards more negative values or more higher values of reverse bias, then the decrease in drain current is slowed down. Uh, this is due to the fact that the curve is a part of parabola. Had it been a straight line, in that case, for every every step variation in the gate and source voltage, the variation in the drain current would have been the same. But since it is not a straight line, but it is a part of a parabola, so for lower values of VGS, with the increase in reverse bias, the decrease in drain current is more prominent, and when it is going to a higher values, then the decrease in drain current will become less prominent. Here are some important FET parameters. So first is the drain resistance. This is the resistance, output resistance or of a FET. Naturally, it is delta VDS, change in the output voltage, divided by change in the drain current or output current, and it is called the drain resistance. The typical value of, just to have an idea of the output resistance of a FET, which is given for 2N3819, the value of output resistance is approximately 20,000 ohms. The value of the drain resistance is very important, because when we are connecting a load to this load resistor to the FET as an output load, then there should be impedance matching. So if we are connecting a load to the output of the FET, then the output resistance of the FET should be approximately equal to the resistance of the load, so that there will be a impedance matching, and only then there will be a complete transfer of power between the FET amplifier and the load resistor. The second important parameter is transconductance or GM, and it is delta ID upon delta VGS at a constant value of VDS, and it shows the value of GM shows the control of input voltage, that is VGS, on the output current or drain current. It means that when GM is very high, the denominator is will be less and the numerator will be more, to make the value of GM high. It means that a slight variation in VGS will make a large variation in ID, or the value of GM will be high. Or in such FETs, the input voltage is very effective in controlling the drain current. And if GM is low for some field effect transistors, it means that the denominator is high and the numerator will be low. That is, we are changing the input voltage by a large amount, but the variation in the output current is not so prominent. And transconductance can be calculated from the transfer characteristics as the slope of the curve. You can see from the transfer characteristics that the slope of the curve is delta ID upon delta VGS. So for different parts of the curve, the slope is different because it is part of a parabola. Therefore, the value of GM is different if it is calculated from different portions of the conductance or transfer characteristics. The third is the amplification factor. Amplification factor is defined as VDS upon VGS, and as we can see, some mathematical rearrangement is done, and it becomes equal to RD into GM, where RD is the output resistance of the FET and GM is the transconductance. Now, another important parameter of a FET is input resistance. Input resistance is a ratio of VGS and IGSS. Here we have calculated the DC input resistance because we have not taken delta VGS and delta IGSS. We have taken the absolute values of VGS and IGSS, therefore it is DC input resistance. As IGSS is a gate current and the gate source junction is always reverse biased, hence IGSS is reverse current and it is very small and it is of the order of nanoamperes. So when IGSS is very small, naturally the input resistance of a FET would be very large, and the input resistance or impedance of FET is very high and it is of the order of several hundred mega ohms. And this is a very important and useful property of a FET, that the input resistance is very large and the output resistance is comparatively small. And the usefulness or the advantage of this property of FET will be discussed in my forthcoming videos.